Again, everybody, I am Garrett Karto Keating, SMA project scientist, and right now I'm going to be talking to you about error recognition. In particular, how do you recognize that there are problems once you've actually made images with interferometric data? So, to start talking about this, I'm actually going to go way back in time to when I was just a wee lad, a mere undergrad, looking up at the skies with the Allen telescope array. And in fact, shown here is the beautiful M33 Triangulum Galaxy in H1. This is actually the very first interferometric image that I ever made. I spent weeks actually working on this image, many hours working through a software reduction package called Myriad. Lots of hard work, and I was very excited, very proud of the image that I made. And of course thinking that there's no way, shape, or form that this image could ever possibly be made better. Of course, that's not true. And in fact, if you look at this image a little bit, you might see that there's some interesting little artifacts here and there. There's some kind of negative bowling here and some kind of features around this bright blob here. And some structure kind of popping around this galaxy that's not clear whether or not that's actually really the image or maybe it's some artifact. And so, looking at this, I think it's a kind of a good example of, where are the areas here that we can kind of pick at and say, all right, maybe we should see whether or not this is an actual problem, an actual artifact of the imaging versus something that's actually just intrinsic to the source itself, and, actual science results. So before we go any further, just again, a brief recap of what it is that we get when we image interferometric data. So typically, when you first actually do the Fourier transform, you get two things. First, you get this dirty image that is the kind of direct output of the Fourier transform after you've gridded all your data. You get the dirty image of the sky, so to speak. And then the other piece that you get actually is what we sometimes call the beam image or the beam PSF. This is the synthesized aperture, or the Fourier transform of the synthesized aperture. This is kind of the pattern that you expect all of your point sources to look like. So with these two pieces of information, you can actually use a deconvolution algorithm, clean being arguably the most popular of them all, and actually construct a model of what the sky actually looks like. And typically, as you're reconstructing this model, you're left over with the residual map that basically, after you have your clean model convolved with your beam image, basically subtract that away from your dirty image and you get out the residual map. So finally, at the very end, you typically have a restoring option where you are stacking the clean model on top of the residuals to get out what's sometimes referred to as the clean map. So in most science experiments, the thing that you're actually going to be putting into your papers and showing at conferences is going to be the clean map, which makes sense because you want to show the interesting source that you're looking at. And also, want to have people believe that this is an actual measurement and not just a model. So you throw in, the residuals to kind of resemble what the noise is doing. In terms of chasing down problems, the most important map out of all five of these, you might guess that it's the clean image, but no. In fact, the most important thing, or the most important map to look at, is actually the residual map. And the reason for that is actually really simple. When you are running deconvolution, you are constructing a model of the sky, and the residuals are basically telling you how good of a model you fit to your data. So kind of similar to how you would run a chi-squared test on a model fit to a couple of data points. The residual map is kind of your chi-squared test of how good your model fit is. That is, how good deconvolution was run when you attempted to run it on your dirty image. So, all that being said, there's one important caveat when looking at the residuals map. And that is that residual maps can actually look like they have structure in them, even though they can actually be completely random. This seems like a strange kind of oxymoron, but it kind of makes a certain degree of sense in that the interferometer, of course, is only sensitive to certain spatial modes. And so when you actually create a dirty image, you only have certain modes of information in your map. So if you have lots of short baselines but no long baselines, you'll notice that these noise blobs will look very fat in size. Whereas if you have lots of long baselines and not a whole lot of short baselines, you'll notice a lot of kind of high frequency, very small structure where things are somewhat correlated in adjacent pixels. That can all basically mean that everything's okay. It's just that you have noise that's correlated from pixel to pixel because your synthesized aperture isn't complete. So the picture is actually pretty close to kind of what you get with different so-called colors of noise. So I've got an example here looking at, so you can actually have, even though you might have noise, you can have noise with differing amounts of basically power kind of on the low frequency side versus the high frequency side. So I'll play right now some what's called brown noise, so there's more power kind of in the low frequency tones. And now I'll play something called blue noise, which is kind of the inverted picture of this, where you have a lot more power in the high frequency tones. All right, sorry if that hurt anybody's ears, but hopefully you realize that, okay, even though those things are both noise, they're both very clearly different from one another. And so sometimes things that are noisy can look like they have structure or something special about them, when in fact it's just kind of a characteristic of kind of the data set that you're looking at. So keep that in mind. We're doing this kind of chi-squared by I approach, but this is always to give you a hint as to what's going on in the underlying problems. You always kind of want to pursue this and look at this more deeply in the actual data itself, rather than trying to completely identify problems with the images just alone. All right, so that being said, what are the kinds of problems that we can run into when we're actually looking at our images? All right, so I have right here a nice big bright point source, something that's about, I've simulated a Jansky source, which is roughly kind of what we expect for a good number of our gain calibrators for SMA. It's a little bit on the bright end. And I've kind of lowered the color threshold here, so I'm kind of zooming in a little bit in color space to highlight some features that are here. You might actually notice that there are these kind of faint symmetric features surrounding the point source here in our cleaned image. And in fact, so this is the clean map. If I just look at the residuals, you can actually see that on opposite sides of the field center where the point source is, I see highly, highly symmetric bumps and wiggles and blobs. And in fact, it's not, it's most significant right around the point source here, but you can also see them kind of off on the sides, kind of way out in the wings of the image, way far away from where any emission is. And it's actually a reasonably significant fraction of the overall flux. It's percentages of the total flux, which with a Jansky source is quite a bit of kind of flux to spill over into other places on the map. So what's going on here? Well, usually when you have symmetric imaging problems, it's pointing towards some sort of problem with amplitude. And in fact, in this particular case, there is an error that exists with the amplitude gains for a single antenna. So if you start seeing lots of symmetric errors, it might be that you actually have an amplitude calibration problem that you need to poke at further and need to look at more deeply. So we just talked about symmetric errors. What about the flip side of that, anti-symmetric errors? So again, kind of same point source, different problem. Again, this is the clean image. You can see, again, that bright point source at field center. It's kind of saturating in color. And then on opposite sides, you might notice if you look very careful at this image, there's a bright spot here, and then there's kind of a negative bowl here. Again, bright spot here, negative bowl here, bright spot here, negative bowl here. We've got completely anti-symmetric components in our clean map. And in fact, if I just look at the residuals, I can see this much, much more clearly, where you've got a lot of anti-symmetric features where bright spots kind of on one half of the map correspond to fainter spots on the other half of the map. So what's happening here? Well, in this case, these are actually antenna phase errors that are producing anti-symmetric features in the map. So you basically, anytime you have a phase error on kind of one side of the UV plane, because of course a baseline has both, each baseline measures a complex visibility that basically arrives on both sides of the UV plane, because of course the sky is, the image of the sky should be real only, so the UV plane is Hermitian. When you have a phase error on one side, it also pops up on the other side, kind of in the exact opposite direction, if you will. And so that gives rise to these perfectly anti-symmetric features when you are looking at your images. So if you see features that look anti-symmetric, so you see a positive bowl kind of, or with a source and field center, you see a positive bowl on one side and a negative bowl on another side. It's usually pointing towards you having actually some sort of phase calibration problem. And so in both of these instances, when you see these kind of symmetric and anti-symmetric problems around your point sources, usually that means you should go back to your gain solution and just check them out, see if things look okay or if maybe there's some weirdness that you need to flag. So, talked a little bit about symmetric and anti-symmetric problems. So let's look at this image right now. Again, we have the same thing. We're looking at, again, the residuals map. So this is still simulating that one Jansky point source at the field center. And again, in the residuals, I see there are lots and lots of symmetric features. This would clearly be pointing towards an amplitude issue. And in fact, if I look at the residuals map and I compare it to the beam map or the beam point spread function, they look very, very similar. So, give you a second to think about what this could be. All right, so this particular issue is actually coming up because we are looking at a point source that actually has a changing spectral, or I should say it has a spectral index, or it has a changing amount of flux as a function of frequency. And this image actually contains many different frequency channels that we're looking at. So you might ask yourself, well, why is this a problem? When we are making images, we are fundamentally assuming one thing, and that is that all of the information in the image is effectively probing the same thing, right? So if you put together data from multiple different frequency channels, or belonging to multiple different days, or multiple different, whatever, what have you, you are assuming that everything is measuring the same thing in the sky. And sometimes that turns out not to be true. That can be true, or that can fail to be true in kind of two general cases. One is that we definitely know that things in the sky change in terms of their brightness as a function of frequency. People who work on spectral lines definitely know this for certain, because of course spectral lines pop up at specific frequencies. But even continuum sources, right? Continuum sources tend to have spectral indices. And so you are averaging together, when you average together over a very wide bandwidth, you can get kind of brighter data points mixed in with fainter data points, and the image that you're reconstructing is kind of sort of having to reconcile between really what is somewhat disparate data, because they are actually measuring different things in the sky. So you can get image errors from that way, from basically averaging together different frequency channels, even though they are at different frequencies. The interferometer is technically seeing a different thing in the sky. The other thing that can happen is that you can actually have point sources that evolve with time. So, and the most common instance of this is that, we know that all of our calibrators in the sky change flux over the course of weeks, sometimes months, sometimes days. And in fact, there are very bright, very compact sources that can actually change their flux over the course of hours, even minutes. Sagittarius star, which is the bright point, the massive black hole at the center of our Milky Way, which is a very bright continuum source. That changes its flux on a course of minutes. And so if you average together data taken on different baselines at different times, and the flux is not stable, you will see these kind of weird amplitude issues, or these kind of weird symmetric errors arising from the fact that different data points are actually measuring different things. They're measuring a different brightness or a different flux coming from the sky. So just be aware that when you average together data, you are making that intrinsic assumption that all of the data are measuring the same thing, and in fact, that assumption can fail. So, some other potential sources of interesting artifacts. Again, I kind of just talked about averaging, but each visibility itself, of course, contains some amount of average information over some both time interval and frequency interval. And as has been discussed a couple of times, over the bandwidth of even a single channel, but typically over a single window, you're looking at multiple different frequencies, and multiple different frequencies actually have, for the same physical distance, have different UV distances as measured in terms of wavelength units. So you can, when you average data, when you have a block of data that you've averaged together, if you have low frequency information merged with high frequency information, you can actually have visibilities that are technically probing different pieces of the UV plane being smushed together. Likewise, when you time average, so here I'm kind of showing, you can imagine kind of cycle to cycle, so kind of red to red or green to green, how much data roughly is being averaged together in each integration. The sky is moving every second, every millisecond, and so over you are, by time averaging even just a few seconds, you are smearing together a little bit of data in the UV plane. Now, typically this kind of issue, observatory staff, of course, know that this is an issue and set integration times, for the raw data to be some reasonable interval. But if in post-processing you were to, say, average over the course of minutes, or for some reason decide to average over the course of hours, you could maybe very quickly see that you'll be averaging data together from different positions in the UV plane and kind of smearing out the results. So, how does this actually end up showing up in images? Well, if I look at, here's my nice good image with everything working just fine. Time smearing is kind of weird because it affects different baselines in different ways. It tends to affect the physically most distant baselines the strongest, but again, it depends on the geometries and the projection of those geometries. And so you'll just end up with a kind of very ratty image where kind of nothing looks quite so normal. Suffice to say, if you've done any sort of time averaging and then your image starts to look worse, maybe it's time to look at whether or not that time averaging was a good idea. Bandwidth smearing, fortunately, is a little bit easier to identify. You'll typically actually see that point sources will start pointing towards the field center. And so if you have all of your point sources pointing towards the very center of your map, it means that you probably have a bandwidth smearing issue. And in fact, you probably need to rethink what it is that you're doing. The most common place to have bandwidth smearing issues is in continuum imaging. There is a technique called multi-frequency synthesis that you can use actually to get around this issue and to actually help out your imaging a little bit. And so if you see these artifacts while doing continuum imaging, you should definitely be using multi-frequency synthesis. All right, so that's kind of the impacts of kind of different choices of kind of different averaging type errors. What other kind of interesting features exist? All right, so here's an example image. I have, again, my nice point source, but then kind of, and I've got a log color scale here to kind of really emphasize the kind of low-level noise here. You can clearly see that this background doesn't look like noise. It looks like a very clearly striped, highly striped pattern. So what is going on here? Well, if you remember back to my first talk, kind of introducing interferometry, if you remember that table of Fourier transforms, this looks like a single sine or cosine pattern, and usually that points towards just a single bad data point. Again, since each baseline is technically measuring two different places in the UV plane, one just being the complex conjugate of the other. That's why it shows up kind of as two separate points in the UV plane, but it's really coming from one bad visibility or one bad kind of small set of visibilities. So if you see kind of a single ripple pattern through your image, it usually means that there's probably a really bad data point. Usually it's a high amplitude bad data point, and so you should actually maybe dive into your visibility data and see if there's any really high amplitude points, because they'll usually stick out pretty quickly. All right, so what else? All right, so here's another image. This one looks similar to the previous image, but it's not quite the same. You again see that there's kind of clearly some sort of patterning here. It kind of almost looks like a fingerprint here, where you've got, it's not one wave pattern. There's kind of clearly some little bending, and it almost looks like there's a kind of a beading pattern that's here, which that's maybe a little bit of a hint as to what's going on. So in this particular image, what is happening is instead of having just a single bad data point, you actually have a single bad baseline. So one baseline tends to probe, depending on the kind of length of the observation, you tend to probe a similar region of the UV plane over the course of, say an hour or two. And so what you're seeing is a whole bunch of modes that are kind of all together that have been contaminated for some reason. And they all belong to one baseline. And so if you see these kind of curvy, almost wave-like patterns, sometimes it actually means that you should inspect the data on kind of a baseline by baseline data or basis and see if there's any outliers. All right, so here is another kind of interesting, weird feature. Again, have my nice point source here at the field center, but there's very clearly some patterning that's kind of going all throughout the image. And in fact, if I look again at the artifacts that I see in the image, it looks very similar to, but not quite identical to what the synthesized beam looks like. So what's happening here? Well, in this particular case, what I've simulated here is actually the effect of what happens if you have just a single bad integration. So this can happen from time to time. Sometimes there are instances where the phase stability gets really poor, or there's a big gust of wind or fog, or something happens where there's a very short interval of time where the data suddenly just become bad. These things can kind of sort of lurk in the data if you're not looking very carefully. In fact, this is usually why I suggest to people that looking at your data as a function of time, both amplitude and sometimes phase, is a very good way of just making sure that nothing weird has happened. So if you see something that kind of looks like kind of not too dissimilar from your PSF, that might be pointing towards a bad integration. And I should say that the reason why it looks kind of like the PSF, of course, is that a single bad integration has a single data point or a single measurement from all of the different baselines. And so usually you have kind of a sort of reasonable facsimile of the UV coverage that you get over the course of some fraction of the track. So yeah. All right. So those are kind of the kind of individual instances that I usually think of, or that I usually try to evaluate. If I'm thinking about, there's something weird in the image and it kind of pops out with these patterns, how can I look at the visibility data? There are other problems or other mistakes that you can make as well. So here again, another clean image, but instead of just a simple point source at field center, I have a couple of point sources. And I notice that there's clearly some patterning that's going around here. And this really doesn't look like that great of an image. All right, so what's going on here? Well, so if I look at the residual map, I will notice very quickly that, in fact, where I have bright emission in my clean map, I also have bright emission in my residual map. And in fact, it almost looks like the flux that was in the dirty map hasn't been completely deconvolved out. So this may be pointing towards a problem with the deconvolution not going deep enough. And so what you're seeing in the residual map isn't a problem, it's just that you haven't basically completed the deconvolution process. So if you see lots of patterning, or if you see a residual map that looks a lot like your clean image, or a lot like your clean model, I should say, sometimes it means it's time to go back to the clean or whatever deconvolution algorithm you're using and to kind of push a little bit deeper. You can do the flip scenario, of course. So here are my point sources, and you might notice here's all these little speckles that you might hope or think are point sources, along with kind of almost what looks like corrugated cardboard here. And in fact, if I look at the residual map, it looks really strange, like lots of values kind of at the very maximum threshold and lots of values at the minimum threshold. This is actually what happens when you over-clean. You'll get these kind of weird artifacts that almost, like, to me, again, looks like corrugated cardboard. And what's happening is that clean is a very simple algorithm, and it can't tell necessarily the difference between an actual point source and just a noise fluctuation. So you are effectively deconvolving noise, which introduces all sorts of interesting artifacts into your residual map. It's kind of hard to do this with kind of more modern techniques, especially with CASA and kind of auto masking tool. There have been tools to kind of make cleaning a little bit more sensible. But if you start kind of driving these processes independently or kind of using some advanced features, you can get yourself into trouble by effectively pushing on the deconvolution too hard. So, probably the last, arguably most common kind of weird feature that I've seen is something that looks like this. So, I've got a clean image that looks really weird. It's asymmetrical. I see there's some sort of something over here, but this map just kind of looks like, it almost looks like waves in an ocean to me. I would not think of this as being some sort of astrophysical phenomenon. This feels like it must be some sort of weird error. So what's happening here? Well, in this particular instance, I have, in the first image, I've only imaged the field of view of the telescope. So I'm only imaging for the SMA that turns out to be about 50 arc seconds across. But of course, especially when you're doing continuum imaging, you can have point sources outside your field of view. And what that means is that while they will be fainter, they will be attenuated by the primary beam response of the antenna. So, the emission that's coming from that direction will be fainter by a factor of a few. They still can be powerful sources of emission. And if you never image so large, if you never make your images so large that you actually see the point source itself, all of basically the point spread function from that source will have this spillover flux that will kind of leak into your map. And, you won't be able to deconvolve it because you don't actually know where the point source is. So if you see kind of some very interesting weird features that seem to almost be emanating from off of the map, it's usually a good idea to make your maps actually bigger. In fact, for this reason, I tend to map at least twice the size of the full width half max of the telescope. So for SMA, I typically make maps that are 2 arc minutes by 2 arc minutes, roughly a piece. On some telescopes, that's just not practical because that makes the maps obviously 4 times bigger, and that's a lot more data to have to handle for what is usually not a problem. Some people I know actually do up to kind of 1.5 times the full width half max. You should definitely do at least 1 times the full width half max. If you go any smaller, you're really you're potentially pushing your luck. So definitely, and yeah, if you see these kind of weird artifacts, you should definitely map bigger. Even if, you just do the simplest kind of, the very simple map or just a continuum map. So, all right. So that's kind of all the tricks that I usually use when I'm trying to look at images and trying to diagnose what exactly is going on and the underlying data. There's one more thing that I think is worth pointing out, which is that when you're running deconvolution, you are actually making a model of what the sky looks like. And of course, once you have a model, you can actually subtract off, not just in the image domain, but also in the visibility domain. You can subtract off that model from the data itself. So kind of in the earlier error recognition talk, I mentioned that sometimes it can be very difficult to diagnose problems because, of course, source emission is very complex. But if you've built a good model and you subtract that model away, what you should be mostly left with should look like noise. And so here's actually a really good opportunity to be able to pull out kind of latent problems in your data, is to actually use a model subtraction method, which I know several of the different reduction programs have tools for doing this. But you can actually, more easily identify a bad time integration or a bad baseline by subtracting things away. Because if you know that something should just look like noise and it doesn't, and you see some big peak, in your data, or you see some weird fluctuation that doesn't match the rest of the data, okay, I need to look at this more carefully. All right, so hopefully that's given you some ideas to how you can use imaging to recognize errors in your data processing. And yeah, thank you very much.